Hi, this is Alex from devstories.eu. OpenCV, Computer Vision, Deep Dive, Episode 15 of 20. Every photograph you have ever taken is a subtle lie warped by the curved glass of the lens. In robotics, that slight warping is the difference between catching a ball and completely missing it. Resolving that gap requires camera calibration, navigating lens distortion. You mount a cheap, highly distorted fisheye webcam on a robotic arm. The system needs to calculate the exact millimeter distance to safely grasp a fragile coffee mug. If you process the raw video feed directly, your geometry is completely wrong. The lens bends the incoming light, meaning a pixel near the edge of the frame represents a dramatically different real-world distance than a pixel in the dead center. If the robot trusts those raw pixels, it will crush the mug. We must correct two main types of lens distortion. The first is radial distortion. Light bends more at the edges of a lens than at its center. This makes straight lines look curved, often bulging outward like a barrel or pinching inward. The second is tangential distortion. This occurs during manufacturing when the lens is not mounted perfectly parallel to the image sensor, causing some areas of the image to look closer than others. To fix this, we need a known geometric reference point. The industry standard is a simple flat checkerboard pattern printed on a rigid board. A checkerboard provides sharp, high-contrast intersecting lines, making it extremely easy for a detection algorithm to pinpoint the exact inner corners. More importantly, because we printed it, we know the exact physical dimensions of the squares. Developers frequently confuse intrinsic and extrinsic parameters when dealing with camera calibration data. It is easy to lump them together as just camera settings. Here's the key insight. Extrinsic parameters do not describe the camera hardware at all. They define the camera's physical location and rotation in the 3D world relative to the scene. Intrinsic parameters, on the other hand, define the internal physical properties of the lens and sensor. They encapsulate the focal length and the optical center. The intrinsic matrix is unique to that specific physical camera and remains constant no matter where the robotic arm moves. The calibration process works by mapping known 3D points to observed 2D pixels. First, you take a dozen or more pictures of the checkerboard from different angles and distances using your webcam. Next, you run a corner detection function over those images. You build a list of where these 2D pixel coordinates land in the images, and you pair them with an array of 3D real-world coordinates of those same corners. The 3D coordinates are just a flat grid based on your known square size, with the z-axis set to 0. You pass both sets of coordinates into the camera calibration function. The algorithm calculates the mathematical transformation required to map the 3D points onto your 2D images. It returns your intrinsic camera matrix, the extrinsic rotation and translation vectors for each image, and a set of distortion coefficients. These coefficients handle both the radial and tangential warp. Once you have these coefficients and the intrinsic matrix, you pass them into an undistortion function. Every new frame your robot sees is mathematically stretched and pulled back into a true rectilinear projection. Straight lines become straight again. Your robotic arm can now measure exact millimeters, reach out, and safely grab the mug. The intrinsic matrix is the foundational layer of computer vision geometry, turning a warped array of pixels into a mathematically trustworthy coordinate system. That's all for this one. Thanks for listening and keep building.